Hello, hello, hello. Good afternoon, Internet. Welcome. Welcome back to another NL Math Man Math Help stream. The same math time and the same math channel. Uh, we are, coming to you live from living on the edge of North America, as it says down below. Because I realized in all the streams that I've done and all the pictures that I've shown and stuff like that, I haven't actually shown any of St. John's or St. John's area, like at any point, right? Which is, that's something I got to fix, right? Because it's easy to take stuff for granted when you're there, right? But I mean, you're not going to be there forever, right? There's going to be a point at which you don't get to see these kind of vistas anymore, and you gotta appreciate them while they're there, I suppose, right? Just because you're living in a place, it's like Zoidberg says in Futurama, right? You spend all the time living in the universe, and you never do these things till someone comes to visit. Anyway, that's a it's a Futurama joke that maybe doesn't. The joke's more for me, really, right? But that's all my jokes are for me, basically. But if you know that episode, that's a good one, right? When someone comes to visit in the universe. Anyway, yeah, this is a picture looking from the top of the trail out of Fort Amherst, going toward Dead Man's Bay Path. This is not actually Dead Man's Bay Path, really, because this is not Dead Man's Bay, I suppose. Although some locally, I think it's still called Dead Man's Bay Path. But this picture is looking from Gunner's Cove across into what they call Freshwater Bay. Now it's ironic that it's called Freshwater Bay because I'm pretty short saltwater, pretty short. I mean, hence why there's an iceberg in it in this shot, right? Like you don't get icebergs in fresh water, right? I mean, yeah, there's probably not a single body of fresh water in the world that would be big enough to have an iceberg in it, right? Like I don't know, some lake in the interior, like on the coast of Greenland, maybe. I don't know. Anyway, um, yeah, so we've got quite a few pictures that I might show up at some point of different vistas of St. John's and the hills around it. It is, of course, a very scenic part of the world over on our little corner of North America, and it is very much it is very much a corner, isn't it? Right? Like just oh boy, hold on, hold the phone, literally, hold on. All right, okay, we got there. We got there. Okay, yeah, I mean it is literally a oh wait, hold on. See? Yeah, we are literally on a corner of North America. Here's St. John's, right? You know, old boy, right? And this is where the picture is taken from, right here. Let's zoom out a bit more so we don't see where my house is, so you can dox me. Oh boy. Um, yeah, so it's looking over this little bit right here, right? And this is Cape Spear out here. And this is the most easterly point in North America. Beautiful hiking around this area. And the trail that I'm on starts from right here in Fort Amherst, down by the gut. In this is St. John's Harbor, right? This is the Narrows right there, right? That's what all our songs are about. When I spies bottom inside the two sunkers, straight through the channels to Coslow will go, right? That's the line. Anyway, yeah, so the trail starts around here, winds up, goes fairly steep up across here, and then this picture that I have was taken from about right here, which is, yeah, about right here, so over near Sandy Bottom, but it's looking out across Gunner's Cove and across this, what is called, as we see here, Freshwater Bay. But like a lot of things in Newfoundland, it is maybe not super accurately named because it is indeed saltwater, right? I've got some other very nice pictures from around here, right? For example, over this side, over from Kitty Vitty, this area over here, over near Pleasantville, this Sugarloaf Path right there. This is a gorgeous trail. I've got some very nice pictures from there that I might show at some point. Although, unfortunately, it does, like, it's very nice in this point and then around Cuckold Head there and in Boulder's Cove. But then once you get up to around here, as you see, it just sort of meets up with a road and then loops back. So, it's a great hike for like the first, I don't know, 60% or so. Then you kind of wish that you had two vehicles, right? You could leave one here and then pick up the other one like up here someplace. But if you got to walk all the way and take the loop, although there's a pole line. There is a pole line that you can take as a shortcut. But still, the pole line is not super scenic either, as you would imagine, right? Like it's electrical poles. But either way, switch on back to my intro screen here. Yeah, this is just a really beautiful shot of some of the vistas, some of the hiking that we have available around St. John's, and it's easy to take it for granted just how beautiful the landscape is, right? And it's yeah, hopefully soon I'll have some pictures from hiking from this year too, and not just need to throw to these ones from like 4 and 5 years ago or whatever. But anyway, today, as we see over yonder, I'm going to be getting to factorials today. Going to be introducing some of those. So that is for Calais' course, although that one is super important for a lot of students. Betty Ann, you will be seeing these in a few courses' time, as will anybody else who's doing the academic program. I think Adam is getting relatively close. Troy, I believe, just finished this course. I think, yes, I think this is the most recent math course that Troy completed. So I think he'll just barely pass needing this one. Yeah, but I mean, you guys know where you're at in your program, right? So this is the first of the grade 12 academics. Although I did mention factorials only recently, right? I even made a highlight of that, right? Of my favorite example of factorials. Maybe I'll brush up. I'll have to mention that again today. We'll see. We'll see. Get into my favorite number, which is 52 factorial. Next up, geometric rotations. Going to do compass method and rotation rule. So then Esther, that'll be a bit more support on how you go about doing those the methods for rotations. I will show again the compass method, and I'm going to do it on some graph paper of my own, so we don't have that sort of like rectangular block issue. Then I'm also going to show you the rotation rule. Now that one is in your notes, in the notes that you were assigned out of the textbook. We don't. The notes from your study guide don't really get into that one because they want you to use the compass method because it is more useful overall. But the rotation rule is still something that you can do a lot of the time if you're finding the compass method to be difficult. Okay. Then after that, I'm going to get on to radicals. I'm going to go over some mixed, entire, and simplified, and solving some radical equations, right? And then the equations are both radical as a noun and as an adjective. That's a terrible joke. It's not really a joke though, right? Because math is pretty radical in general. So first up, I am going to introduce factorials. So factorials, I want to start off with, let's see, let's start off with the study guide here. So let's switch on over to the document display. Here we go. Oh, and let's straighten up my doc cam. There we go. That's better. Paper was a bit off. Okay, so Calais, in your so your unit 2 begins with factorials, right? And it talks about counting methods, right? But really the first math that you will see, or the first type of working that you will see in this unit is going to be factorials. Now, it says factorial notation is a concise representation of a product of consecutive descending natural numbers. Now, what in the heck does that sentence mean, right? So this is Math 3102A, Unit 2. Oh, I'm zoomed in way too far. Way too far. Not usually zoomed in that far. Oh, yes, that was from yesterday, I guess, where I was, yeah, when I had it zoomed in super close on the, no, it couldn't have been, because I've moved it since then. Anyway, whatever. It don't matter. None of this matters. So factorial. So a natural number, rather, a number factorial is that number multiplied by all natural numbers or positive integers lower than itself. Okay, so this is really the exact same thing that your notes are saying there, but I'm going to maybe walk through it a bit more so you can see kind of what's going on. So for example, like 5 factorial, well, what are the natural numbers? So it's that number multiplied by all natural numbers lower than itself. So that number is 5. And what are all the natural numbers lower than 5? Well, we know that natural numbers are integers, and natural numbers are only positive integers, right? Because you can think of like in nature, you don't ever see zero of something, right? I mean, you're seeing zero of everything all the time. Like I am seeing zero dinosaurs in this room right now, you know, right? Zero tigers, right? So that's to say that the tiger repellent that I bought is doing a really good job because there's no tigers around, right? But still, in sort of a natural representation, there aren't any, right? So it doesn't kind of make any sense to say that there's zero of everything that I don't see around me, right? So the natural numbers are positive integers. And by the same token, right, you generally wouldn't say, oh, I see 1.5 tigers in this room, right? Unless, I mean, we're not going to get into grisly situations like it was, you know, half eaten or something like that. Okay, maybe that was a poor example. But my point is, natural numbers are sort of things that you would see in nature, so it's always going to be positive whole numbers of something. So all the positive whole numbers smaller than 5 are, of course, 5, 4, 3, 2, and 1. Now we are multiplying it, so you needn't always write out 1 because times 1 doesn't do anything. And of course, then factorial has to stop at times 0, because if we did times 0, then anything factorial would just be 0, and there wouldn't be any point in doing it, right? So 5 times 4 is 20, right? 20 times 3 is 60. 60 times 2 is 120. So 5 factorial is 120. Right? But what does this tell us? What does this tell us sort of in the real world? Why is this under a unit called counting methods? Right? What in the world are we counting when we're using factorials? Well, right, so factorial counts the number of different ways to order a set of objects. Now, before, when I was talking about factorial, see, I'm getting into it right away. I'm getting into it even quicker than I thought I was going to. I talked about how the number of ways to order a deck of playing cards is like an 8 with 67 zeros following it, right? It's a gigantic, ridiculous, huge, massive number. That means that you know, every single time we shuffle a deck of cards, a deck of 52 playing cards, it's statistically likely that that is the first time that order of playing cards has ever existed in the history of the world, right? And that's because 52 factorial, or the number of ways we can organize 52 different things, is just so massively bonkers big. But say even that we had 5 playing cards, just 5, just like a random hand of 5, right? That's a I mean, that's an okay hand if you're in 5 card draw, right? I guess you're gonna pitch 3 then, right? But say we were in like, oh, triple draw low. Triple draw low, this is a killer hand. Look at that. Triple draw low, right? You keep those 3. You're drawing to a 6. I mean, you're drawing to a 6-5, right? But still, that's pretty good, right? Like for a first hand, I mean, you'd raise with that. Um, anyway, so with 5 cards like this, there, even though it's only 5 cards, like 5 cards is not very many, there's actually 120. 5 factorial, there's 120 different ways we can organize just 5 cards, right? Because we can put this ace first, and then we can have this is one order, or if we switch this is another order, then we switch this is another order, switch this is another order. You see what I mean? Like there's 5 options for the first card, 4 options for the second card, 3 for the third card, 2 for the fourth card, and then 1 for the last card. I went out of my camera. But so factorial counts the number of ways that we can order a set of objects. And that's why factorial is going to be super useful in these things that we're going to see in a bit that are called NPR and NCR, which are ways to do permutations and combinations. So that'll be sort of the major topic for this unit that you're getting into, right? Anyway, that's just a little aside over here that I do like to keep mentioning. That this also involves scientific notation, right? Which is another topic that we're not really getting into right now. So I'll spare you that. I'll spare you the whole diatribe about that. But you can watch it in my stream highlights if you really want to see me ramble about, you know, how much complexity there is in a system that looks as simple as a deck of playing cards. So factorial counts the number of ways to order a set of objects, right? And we are going to see that in a bit. But for this first unit, we're not actually super duper concerned about that. We are more concerned about just how we're going to go about doing the sort of arithmetic, or the algebra rather, sorry, not the arithmetic, but the algebra that we can do using this type of math, right? So let me then skip over. You asked to do questions on page 79. So let me skip over here. Oh, no, that's not the right book. Yeah, here we go. Okay, so you were looking at ones, Kelly, like these ones here on page 79, right? So the ones you mentioned to me were these questions up here. I'm not going to go down through those ones directly because, of course, you do have fully worked through examples of all of those that are just totally available to you whenever you want them. So, these pages here. So it might be more useful for me to go down through some of the ones that you don't have examples for already. So I'm going to skip over here to page 82, and I'm going to do these questions. I'm going to do questions 5 and 6 here, or at least parts of them. So let's zoom in on all of these here. So these are some good questions to see some of the properties that factorials have, right? So this is page 82. It's going to be question 5A. All right, so for 5A, we're doing 8 times 7 times 6 factorial. Well, you will see them write stuff like this sometimes, but it is important to know that we can break factorials apart, right? And we can put them back together. Because we know that 6 factorial, well, we know that 6 factorial is the same as 6 times 5 times 4 times 3 times 2 times 1, right? So we could easily say that this could equal 8 times 7 times 6 times 5 factorial. Or we can say this equals 8 times 7 times 6 times 5 times 4 factorial. We could say all that if we wanted to, but none of that is really making it any simpler, right, to evaluate. We could just as easily say that this all equals 8 factorial, right? Because we're already doing out the factorial here. 8 times 7 times 6 times 5 times 4 times 3 times 2 times 1. And you can do those manually if you want, right? But doing them manually is going to take you a bit of time sometimes because we might have some fairly big ones for you to evaluate. So what I'm going to recommend you do is find in your calculator where the factorial function is. Now it'll be different for every different calculator, but here in my TI-84, it's over here under math, and then probability, which is over here. Oh crap! I didn't mean to put in rand int. 8, and then I go to math, go to probability, and you see down through here, these are also functions that we're going to use in this term, in this course. But down here now, this exclamation, that's what we want. And we see, look at that, 8 factorial is 40,000. 5 factorial was 120. 8 factorial is freaking 40,000. 320. Wow. Right? And you see how factorials grow so quickly that as you keep adding more and more and more items, basically, to a set, you can rearrange them in so many different ways. That's why when we get to 52 items, the number just goes like, whoa, crazy big, right? An 8 with 67 zeros, right? Like a number that would take you, I don't know, a solid like 3 or 4 minutes just to write out, and another minute or two to count and make sure that it was actually 67, right? Like crazy. Anyway, but that's just the way that 8 times 7 times 6 factorial is that's just 8 factorial, right? Yeah, let's keep on going for these ones because these are important questions. You are going to see quite a few of these sort of properties later on. 5b then, 12 factorial over 10 factorial. Well, this is another super important property of factorials, is that we can cancel them. Because what is 12 factorial? What's another way we can write that? Well, that's, of course, 12 times 11 times 10 times 9 times 8 times 7 times 6 times 5 times 4 times 3 times 2 and times 1. Right? I could write out all that if I really wanted to. You're not expected to do this to answer this question. I'm just doing this, of course, as an illustration to show you what we're actually doing. And 10 factorial is 10 times 9 times 8 times 7 times 6 times 5 times 4 times 3 times 2 times 1. And we know that when we have all the numbers up top are multiplied together and all the numbers down bottom are multiplied together, we can cancel ones out, right? So like this 10 can cancel with this 10, and this 9 with this 9, and 8 with 8, and I think you're seeing where I'm going with this now. And the ones don't really need to cancel, do they? Because they're 1. But we're just left with 12 times 11. So we are left with 132. Another part of my times table that was ingrained into my brain by Math Blaster. Right? I actually looked up Math Blaster to see if I get like the classic one to play it on stream a bit. Maybe I'll see if I can find that. But like the newfangled one that's like a web-based one, I don't know. I don't know. Maybe it's great, but it's not what I was. It's not what I wanted. It's not the it's not the memory one that I have. But anyway, so we can cancel out of factorials just like that, right? So say if we had a one like 5c, which I'll do down here. 5c is 8 factorial over 2 factorial times 6 factorial. Well, we know that 8 factorial is 8 times 7 times 6 times 5 times 4 times blah, blah, blah. And 6 is 6 times 5 times 4 times 3 times 2 times 1. But 8 factorial, we knew up here, right? We were told that literally in 5a, we looked at this, that 8 factorial is the same as 8 times 7 times 6 factorial, right? So let's write it in that form. 8 times 7 times 6 factorial over 2 factorial times 6 factorial. And we see now that we've got a 6 factorial on top and a 6 factorial on bottom. So those guys are going to cancel with each other. Boom, boom, gone. We're going to be left with 8 times 7 divided by 2, because of course 2 factorial is just 2 times 1, which is 2. Then of course we can cancel that with this 8 and call it a 4. So what we're left with is 4 times 7, 28. Right? Let's see. Yeah, I'll do some of these other ones a bit quicker, but I do want to give you, some more background with these to show the way that we're going to do them. So we know that 6 factorial is the same as 6 times 5 factorial, right? And then the 5 factorial is going to cancel with the 5 factorial. We're going to be left with just 7 times 6, going to be left with 42, right? Simple stuff. Well, I mean, simple once you get the topic, right? Once you're already sort of introduced to it. Yeah, I'll keep doing number 5, then maybe I'll do most of number 6 as well, because 6 is more similar to what you asked for. But I am going to finish off number 5 here real quick. So we've got 6 factorial over 2 factorial, 2 factorial, and that whole thing is times by 4. But of course, when we think back to our order of operations, just BEDMAS, we know that we're supposed to simplify what's inside our bracket before we go about trying to move on and trying to, incorporate what's outside the bracket. So that's going to be the same as 4 outside of, well, this is 6 factorial divided by 4, right? So that's just going to be 6 times 5 times 4 times 3 times 2 times 1 divided by 2 times 2, right? Which is going to be the same as 4 outside of 6 times 5 times 4 times 3 times 2 over 4. I'm not going to write in the 1 because, of course, times 1 doesn't do anything, right? The 4 can cancel with the 4, or that 4 can cancel with that 4 outside there, I suppose, right? I could do this either way and do 4 times 6 times 5 times 3 times 2. So that's 30, right? 30 times 3 is 90, times 2 is 180. 180 times 4 is going to be 720. There we go. And then F. You get F's in chat. F is going to be 4 factorial plus 3 plus 2 plus 1. Now, unfortunately, for adding factorials, there's nothing really fancy that we can do, right? We can't put these all together any way other than just figuring them out, right? 4 factorial is 4 times 3 times 2 times 1, so that's going to be 24, right? 3 factorial is 3 times 2, which is 6. 2 factorial is 2. 1 factorial is 1, so that's going to be 33. Right? That's all we can do. All I can do for that one. Yeah, I'm not going to try to cram question 6 in on the same page. So let's go ahead and grab a new page for moving on to question 6 here. And Calais, this question 6 is fairly similar to the ones that you were asking about. The other ones I wanted to do sort of as some background. This is Math 3101A, Unit 2. Yes, it was Math 3101A. Right, that's what I should have written on the previous sheet. Oh well, that's mostly just important for me, right? So, question 6 then. So we have n factorial over n minus 1 factorial. Now, one reason I really need to go down through this question is because you need to get a grasp on sort of what this is all representing, right? Now, no matter what number n or n minus 1 is, this all works out to be, we can still simplify this one down quite a bit, but it's, excuse me, boy, but it's because of what factorials represent, right? Remember, like I said before, a factorial, like say, 5 factorial is 5 times 4 times 3 times 2 times 1, right? You know, I don't know, 7 factorial equals 7 times 5. 7 times 6 times 5 times 4 times 3 times 2 times 1, right? Say we had, oh, I don't know, 142 factorial is 142 times 141 times 140 times 139. I'm not going to go through and write those all out because I'd be here a long time, but it's going to eventually get to times 3, then times 2, then times 1, right? So, by the same token, we can say that n factorial, any number factorial, is the number itself multiplied by the number minus 1, multiplied by the number minus 2, multiplied by the number minus 3, and then so on down to 3 times 2 times 1. Right? And this part here, this sort of notation, this is super important for what you're doing there now. This is sort of the crux of understanding the algebra, like you'll see in question 6 here, and like is for the examples in the textbook that you asked me to do questions like. Boy, ended that one with a preposition. Yeah, I'm not scripted, right? I don't have a teleprompter here. So yeah, no matter what number n is, we know that factorial of n is going to be the number times the number minus 1 times the number minus 2 times the number minus 3, so on and so on down to 3 times 2 times 1. So how can we use this property to help simplify this expression over here? Well, I know that n factorial, the one that's on the top, like I just wrote out, is n times n minus 1 times n minus 2 times n minus 3, so on, times 3 times 2, and then times 1, right? And the one below it, n minus 1 factorial, that's going to be n minus 1 times n minus 2 times n minus 3, all the way down to 3 times 2 and times 1. So now you might be seeing, well, it doesn't actually really matter what n is. There's still a lot of canceling that we can do here, right? Because this n minus 1 can cancel with this n minus 1. This n minus 2 can cancel with this one. This n minus 3 with this one. This 3, this 2, and this 1, and so on for all the ones that are sort of encompassed by our ellipsis here. So no matter how big n is, whether it's, 7 or 8 or 492,000, right? We're still going to be able to cancel everything except for that n. So the answer to 6a is simply just n. No matter what n is, n factorial divided by n minus 1 factorial is going to go back to being that same number. Right? Let's see if, let's cram b in over here along the side. All right, so b is n plus 4 times n plus 3 times n plus 2 factorial. Well, and what is n plus 2 factorial, right? So let me just write out what this full thing would be. Well, it would be n plus 4 times n plus 3 times n plus 2 times n plus 1 times n times n minus 1 times n minus 2, and so on, down to 3, 2, and 1. Now I'm doing these on 2 lines here, not because I didn't put a line in between because these are not actually divided. This is all just on the side. I've just ran out of space, right? So we can see that we kind of start off with n plus 4, right? Because no matter what n is, we start off with the number n plus 4. So if n is 8,000, this is 8,004 times 8,003 times 8,002 times 8,001 times 8,000, 7,999, 7,998, so on and so on, all the way down to 3 times 2 times 1. So quite simply, we can just call this one n plus 4 factorial. Right? Because these are all multiplied together. Factorial is a function, right? But it is sort of another way of representing just a series of multiplications, right? So here, even though the factorial was only on the n plus 2 from the start, we can still encompass these n plus 3 and these n plus 4s into our factorial and call the whole thing n plus 4 factorial, like so. Excuse me. Yeah, let me carry on here. I'm going to do, yeah, I'll do the rest of question 6 probably, because question 6 is a good one because it shows off a lot of the common properties of these. And at the point where these ones in question 6 seem easy, I think that means that you've started to really grasp what this first part of the factorial unit is meant to teach you, right? So if you're looking at me doing these and think like, boy, why is he spending all this time going over these? These are easy. Well, great, amazing, right? That's exactly where I want you to be by the time you finish this unit. So this is n plus 1 factorial over n factorial. So again, I'm just going to expand these a little bit so we can see what we're doing. N plus 1 factorial is the same as n plus 1 times n minus 1 times n minus 2, and then so on to 3 to 2 and to 1, like that, right? Because we're always going down with these numbers, right? So it goes from n plus 1 to n minus 1 to n minus 2. A common place for people to make mistakes in this is to think, well, this number is going up, right? This goes from 1 to 2 to 3, so if I see n plus 1, my next one needs to be n plus 2, and my next one needs to be n plus 3, right? But the point is, it's not that this number is changing so much as this whole number is going down by 1 each time. And it has to be going down, obviously. Because if we're going up, we're never going to get to 0, and it would be infinitely long, and every answer would just be I mean, the answer would be infinity, like without even a limit, right? So yeah, we're always decreasing numbers when we're doing factorials. So n factorial is n times n minus 1 times n minus 2, 3, 2, 1, right? So I mean, I think you're seeing where I'm going with this now. Cancel, 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 cancel. The answer is just going to be n plus 1. Right? Then for, let's see, for D over here, like this, it's going to be n factorial over n minus 3 factorial. N minus 3 is it's a bit further down than we've been dealing with yet, very much, but let's see what happens when I expand these guys. So n factorial is n times n minus 1, n minus 2, n minus 3, n minus 4, so on, 3, 2, 1, right? Then n minus 3 factorial is n minus 3 times n minus 4 times n minus 5, and so on, down to 3 and times 2 and times 1, like that. Okay, so now we can see that this n minus 3 is going to cancel with this n minus 3, 4 with 4, 5 with, well, there's a 5 in there. I just didn't write it out because I'm not always going to write out all of those. And we see that what we're going to have, once we're done, is n times n minus 1 and times n minus 2. Just like so. Right? Yeah, I'm going to go through the next two as well. Like I said, just to do out these ones relatively quickly. E, we have n plus 5 factorial over n plus 3 factorial. I'm going to do this one sideways because I'm running out of space here. which is n plus 5 times n plus 4 times n plus 3 factorial, divided by n plus 3 factorial, which is going to be, this is going to cancel with that, it's going to be n plus 5 times n plus 4. Now this, what I've just done for question E here, is more like the way that I would want you to represent the working when you're doing a question like this, right? So n plus 5 factorial, you don't necessarily need to do out all this dot, 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 3, 2, 1 stuff like I've been doing for these ones. I'm doing that because I want to show you really the sort of the reasoning behind these questions. When you're doing them yourself, you can just leave this as n plus 5 times n plus 4 times n plus 3 factorial, and the bottom has n plus 3 factorial, so this number cancels with this, and we're left with just those two multiplied together. Now, you needn't go through and FOIL this out, right? You could go through and call this n squared plus 9n plus 20, right? You could if you really wanted to. I'm pretty sure your book, I don't have the answer key in front of me, but your book isn't necessarily going to expect you to do that. I wouldn't. But you could. The problem with doing an extra step that you don't necessarily need to is that it introduces another way to make mistakes, right? So maybe don't do that one. Just leave it as that. And I mean, to be honest, you could do that for any of these ones, right? I could have expanded up here, or yeah, these other ones. Well, that one I ain't gonna expand. That one's gonna take a little while. You never get to the end of it, right? Anyway. One more on these, and then let's see. Then I should be ready to start some rotations, I think. So this is going to be n minus 2 factorial over n minus 1 factorial. Now, f is a good one to do here. F is an important one because this one again shows some of the common mistakes that students make. This one starts off at n minus 2, and this is n minus 1, and you might be used from all these ones to seeing there being something left on top. So you might glance at this and think, oh, I know what that is. That's n minus 2 times n minus 1 times n. Right? No, it goes the other way. Right? This is actually n minus 2 times n minus 3 times n minus 4, and then so on to 3 and to 2 and to 1. Right? It's like down below, n minus 1 factorial is actually n minus 1 times n minus 2 times n minus 3, and so on, down to our 3 and our 2 and our 1, like that. Right? So now, what can we cancel? Well, we can cancel the 2, n minus 2 with the n minus 2, the 3 with the 3, the 4 with this stuff, 3's and 2's and 1's. And we're left with 1 over n minus 1. Like that, because they're n minus 1. The part that's left over is actually on the bottom this time. Right? But that's totally valid. It's totally fine to see that sort of thing in a question. So, Calais, I hope that was useful for you. Stream starts soon. No, it doesn't. It's going. Take another look at our beautiful shot of St. John's hiking from a few years ago. Next up, I am going to switch over to geometric rotations. We're going to talk a little bit about compass method and rotation rule. Let's see. I'm going to do pages. Yeah, I'm going to bring up the pages from the study guide and from the textbook. So, Esther, if you're there and if you have your textbook, I'm going to talk to you about pages, let's see here. What are these? What are the page numbers? 304 we're going to start on. Page 304 in your math textbook. And go on over here, and that's going to look a little something like this. All right? So first up, they talk about doing the rotation method, right? So we've got two parallelograms here. You're here? Okay, great. Yep. Welcome aboard. So the book walks you through these ones, which are, it is a pretty good example here in the book of sort of what your working should look like. And you notice here on this page in the text that the arcs that they draw start at each of the vertices or the corners of the shapes, and they sort of continue, right? So this is like a partial circle where the radius of the circle is the distance between the point of rotation, which here is the origin, and the point at which we're drawing. But you can think of it like a circle, or you can think of it as an arc that sort of starts here and then just continues down around, right? But you notice there's one arc from each of the vertices, right? Then after they draw their arcs, what they do then is you draw a line, a straight line, from the point that you're rotating to the center of origin, and then from there, you draw your angle. So they happen to be rotating at 90 degrees clockwise, and clockwise is, of course, this way, right? So they're rotating it from there 90 degrees down that way, right? So this is how the shape ends up. It sort of turns to the side, right? So I'm not going to go through that example directly because you've already seen that one. I'm going to talk about this as well, rotation rule, but I'm going to talk about that in a second. First, I want to show some examples of doing this one. So I'm going to go down and do a few examples here with the compass and protractor method. And the thing about the compass and the protractor method is that it can do questions like B and C here, right? The rotation rule that I'm going to show you a bit after this can't. It can't do question B and it can't do question C because these questions, 45 and oh sorry, no, it can do this one. Never mind, my mistake. It can't do question B. Oh goodness, I gotta. Oh boy. Yeah, so I'm gonna do at least A and B out of this set here, so you can see sort of a bit more about how the compass method works for rotations, and then some of the strengths of the compass method, I suppose, as compared to the rotation rule. And I'm going to show you the rotation rule after, which is it is a shortcut. It's a shortcut that works just fine as long as we're rotating it multiples of 90, right? As long as we're doing either 90, 180, or 270, we can use the rule, the rotation rule. But if we're doing it by any other amount of degrees, then we can't. Which is why you do need to know the compass method as well, because it's entirely possible, entirely likely, nudge, nudge, wink, wink, that on your test you might be given a 45-degree rotation, which you can't actually do with the rotation rule. Right, so I'm going to do, yes, this is going to be 4A. Tell you what, maybe I'll draw a separate coordinate plane each time. What am I doing? I've got enough graph paper for that. Boy, I can splurge a little bit, right? So 4A, I'm going to do down through here. So the shape, it's quite a complicated shape there for 4A, and this is page 309, right? It says 309 in the corner. Yes, 309 in the corner of my PDF. I was making sure that 309 was actually the page out of your textbook because that matches up to my PDF. So I'm going to just redraw this shape here. See this guy over here? So it's going to be 1 and then 1, 2, 3 right there. And then the next one is 1, 6 up there. And then let's see, 5, 5, 3. 5, 3 for point Z, point Y, point X, and point W. Boy, this shape's got a few pieces to it. There we go. Okay, this is our original. So I'll color this guy in just a light shading of black there, so we can see this was our original shape. Okay. Now point T, you'll notice for this one that we're not actually rotating this one about the origin. We're rotating this one about point T, which is right there. Right? So the way that we're going to go about doing this, we're going to take remember the steps that I mentioned yesterday and that I sent you an email earlier listing out the steps as well. But our first step is going to be to make our arc, right? So I'm going to get my compass and my pencil. I'm going to load that up, get that in there, screw that in fairly tightly. Now this point here, the spiky one, that's going to go on the center of rotation. So that's going to go here on point T, corresponding to the shape. And then this other point, the pencil lead, is going to go on directly on one of the points on the shape, like there, like so. All right, let's see if I can get, yeah, there we go. See if I can get it on a bit of an angle there for you so you can see a bit better what this looks like, right? So right now, as you see, this point is on the center of rotation. This point is on the part of the shape that I'm going to be rotating. Now I'm going 90 degrees counterclockwise, so I know counterclockwise is this way, so I'm going to need to make my arc in sort of that direction as well, right? So I'm going to start off making my arc, putting a bit of pressure on it, but not a lot, because I don't want it to move. Well, I do want it to move, I just don't want it to become narrower or wider, right? And I'm going to trace it back over to make sure I've done that one correctly. There we go. Okay, so that is my arc drawn for that guy. So that was our first step, right? Was to draw our arc. Our second step then is going to be to draw a line from the point to our center of rotation, right? So our point is here that we were moving. Our center of rotation is here. So I'm going to draw a straight line to join the two of them, like so, right? So there's the straight line that I've drawn to join the two of those. Now remember, our third step is to get our protractor, which I've got over here. I've got a 180-degree protractor. And now I'm going to draw my 90-degree angle. All right, so I have to make an angle that's 90 degrees with this line that I've just drawn. So we know how to position our protractor. We did see that in some previous courses, right? This part here, this sort of like crosshair bit. So this bit, that's got to go on the vertex, right? That one there. And then this bottom line across here has got to go lined up with the line that we just drew. So that's going to look like kind of like that. Yeah, there we go. Got to lean over a bit to make sure that I'm getting there. And now we want to go to 90 degrees. So 90 degrees is here. We're going to take our pencil and we're going to put a little notch up here, right? Just to show us that that was where the 90-degree angle was. Then we're going to take a straight edge. I'm just going to use the bottom of my protractor. And we're going to join that 90 up like so. And there we go. Now we got there. We've got to where we need to go, because the point that once this point here, which was point Y, right? Let me label that one. That was point Y over there. Once that rotates, and we call it Y prime, it's going to be right here. So Y prime is going to be right there, right? Because that's the cross of those 2 points. Now, technically, what you're supposed to do is rotate every single point on the shape this way. Now that takes a bit of time, doesn't it? But you are going to have to do at least, I would say, do at least 2 or 3 from every shape, and then maybe you might be able to see how to join it up afterwards with the other points that you've rotated. But I am going to do a few others here now. I'm not just going to do that one point Y. So let's do point U as well. So point U is this one down here. So let's rotate point U so we can get U prime. Remember, step 1. Right, let's see, if I write my steps out over here. I'm not going to write it out in a ton of detail, but step 1 is the arc, right? So I'm going to go this point, center of rotation, this point, vertex of the shape, right? An arc from the center of rotation and the vertex, sort of like so, right? And again, I'm going to get in there, get real in there. Really, really get in there. Come on, camera. There we go. Sorry about the seasickness there for that one there, guys. We're on rough seas here, right? I showed St. John's in the picture at the start, so it's only thematic for us to have some rocky seas, right? But there is how it's going to be positioned. This point is on the center of rotation. This point is on the vertex. Now I'm going to take this and I'm going to draw my arc, and I'm going to go in the direction, because I know counterclockwise is the direction I'm rotating this guy, and it's going to go chug it, chug it, chug it, chug it, chug it, over here like so. Right, now I'm going to have to ignore that other line. I'm going to have to ignore this one that was drawn, because that's not the one that we're going to be using right now. It's going to be slightly different. Boy. Oh, my camera has been jostled a touch. I think it's pretty good that the boom cam setup can withstand that sort of like repositioning on the fly. I think it's pretty good for this DIY sort of setup. Although it is a fairly nice desk lamp. I've had this desk lamp for years and years and years. This desk lamp, I think I got that in undergrad, maybe. I remember having this for a really long time. Like I've had this one since, I would say, like 2004 or so. So now what I'm going to do is step 2. Draw a line between the vertex and the center of rotation. So that is here like I'm showing right now, right? The vertex was here, this U. Center of rotation was this one here, which was marked T originally. And I'm going to draw another line there like so. And now that one is directly horizontal, right? Despite how I drew it just then, that one is directly horizontal. So we know that 90 degrees is going to be directly vertical. But I'm going to make a good show of it. And I'm going to show you that we do indeed have to measure it, right? And we do see, hey, look, 90 degrees is actually just directly vertical, because of course it would be, because it's a right angle. Then we're going to take this and draw it like so, draw our line. And then where this line, where that angle matches, we're going to be good. So step 3, draw an angle from the line in step 2, right? And that one's going to go up like that. And then step 4, where the angle in step 3 crosses the arc from step 1, we draw our new point. Right, so we're going to draw, oh, yeah, I was a little bit off there. You missed some of those words maybe, but you'll see them all, of course, on the notes that I send. So then, once it crosses, and we see it crosses right here, so that is now going to be our new point. So this point here is U prime, which is to say point U after it has been rotated. Right? So let's do a rotation for one more point, and then we'll sort of check and make sure by repositioning the shape manually. We're going to see if we're getting what it should kind of look like. So I'm going to pick point W, a gold W. I was at the improv, and I wasn't doing very well, so they decided to add an E. It's another Mitch Hedberg joke. Butchering Mitch Hedberg's material on stream. I was going to say daily, not daily. Probably like once a week, though. Once a week for sure. Now I'm going to, okay, avert your eyes, Twitch chat. We're going to move in. We're going to move in. Here we go. Here we go. There we go. Yes. Yes, look at that. Look at that technology, right? We can do it. So now we see that this is the point of rotation here. This is the point on the shape that we're rotating from. Now I'm going to draw my arc going counterclockwise like you do, because that's, oh boy. See, therein lies some of the problems. See, I wasn't pushing down enough on the pointy bit. So there we go. There we go, good. That's how it's supposed to go, yeah. There's our arc. That should be enough. Yeah, okay. So there is our arc from point W. Okay, let me straighten back up again. Not bad, right? It's smooth. That's like Steadicam stuff, right? maybe not. Maybe not quite a Steadicam. Right. So I'm a little bit skew there. There we go. That's a bit better. So now we're going to see from here over, we made this arc. Now again, I'm going to draw my line right from there to the center of rotation. This is going to be step 2. Step 2 of the rotation process is to draw said line like so. Now I'm going to draw the angle. The angle that I want to do is over here like this, 90 degrees. Put that one over here. Draw my straight line like so. Where does it cross? It crosses right here. Hey, look, it crosses directly on a point too. Looks like I was doing a fairly good job of rotating that guy. So this one is now W prime, right? And you might be now starting to see, well, we could start putting together the shape and seeing what it looks like, right? And it is important when you're doing rotations like this to be able to sort of envision what the shape is going to look like after you're done. So what I recommend to do is what I said yesterday, right? Take a pen or something like that and put it on your point of rotation and literally turn your pen. What we can do to sort of get a preview of this is we can put our pen or something like that here on our center of rotation, and we can actually just turn the whole sheet, right? We can just sort of turn the entire sheet, and that then will give us a preview. Hey, look. Okay. So now we can see that once we've rotated it 90 degrees counterclockwise, it's going to look kind of like an L, right? Well, a backwards L. A J. More like a J. All right? So we know now sort of what our shape is going to look like, and we've got several points. So I think we should be prepared now. We can go and start joining this one up. We know that from U, the shape will look like sort of like this, right? There we go. And that matches up with the other points that we've drawn on here. Shade that in there like so. Like that. There we go. Right, so that is the shape now after we've rotated it, and we've rotated it, like I said, with the sort of the rotation method, right? So let's look at, I wanted to do B as well here, and I wanted to do B because this is a 45-degree one, and we can't do 45-degree rotations with the shortcut method that we'll see in a bit, but we can do the other ones. Well, we can do 90s and 180s. We can't do every angle. We can do every angle with the compass method, like I've been doing here, right? So, again, I'm going to draw out. I'm going to try to get that big smudge there to be under my under my coordinate grid, so I'm not wasting paper because I'm using such heavy ink here. But I want to use the fairly heavy ink so that it shows up well. Okay, so for this question over here now, our points are 2, -1, right there, 2, -3, so right there. It's going to be 5, -2, 5, -2 right there, and then 4, -4. So 4, -4 is going to be right there. So those are the 4 corners of this shape in part B. This is S, R, U, and T here. Okay? I'm going to go through this one a touch quicker than the previous one, but this is still page 309. And this is question 4B. Right? So, I'm going to get my compass. Set it up. The point of rotation is, oh, what is our center of rotation? V, yes. Our center of rotation is right here, which is V. So, you can zoom in a bit and see it. Point on the center of rotation. This point on the vertex of the shape that I want to rotate. Then I'm going to draw my arc. Now we're going 45 degrees clockwise. Clockwise is, of course, this way, right? So I'm going to draw the arc the direction of my rotation, like so. Keep my paper decently flat. Draw my arc over like so. And there we go. So that's an arc for T there, right? We'll stay zoomed in a bit maybe so you can see more clearly what I'm doing for these next few parts as well. So now, between the center of rotation here and between the point there, we're going to be drawing a line like so. There's our line. Now we need to measure a 45-degree angle. You need to measure a 45-degree angle sort of over from here like this, right? Because we know that this is the center of our angle, so that's where the corner, sort of the crosshair sort of our protractor needs to go. The line on the bottom of our protractor needs to line up with this line that we've just drawn now. So it's going to look sort of like so, right? And then I'm going to need to find 45 degrees. 45 degrees is over right here, right? That's where 45 degrees gets us. So now I'm going to draw a line between those two. There we go. So our new point T is going to be right there. Now, we don't need necessarily to have that be on a whole point, especially when we're rotating by angles other than multiples of 90. Oftentimes, we're not going to get this exactly on part of our grid, and that's just how it's going to go. You know, we're not always going to get that. So I'm going to keep doing these other ones, and as you're seeing, I'm going to go a little bit faster than I was before. Let's do point U here, right? So again, right? See what I've got done? Right? This one here, whoa, shook it a bit. This one here is on the center. This one here is on the vertex. We're going to take it and I'm going to draw an arc. There's that arc, right? Now I'm going to draw my line between point U and point V, so between the vertex and the point of center of rotation, like so. Then make an angle from that one, line it up correctly, like so. Draw my angle over here, because this is where 45 is, we can see. So 45 is down here. You can see that. Then we're going to take that, join it up like so. And now the one that we're looking at is this line over here. So this is now going to be our point U prime here. And this was point T prime. Right? Once we take those and rotate it. Now, again, right, I'm going to model some good behavior here. So I'm going to go ahead and do this different measure for all of them. Let's do, I'm going to keep using the pencil here. So this is a really small one in here, so I might need to change where my pencil is going to be. They're sort of like that, right, like this. I'm going to draw my arc like so. This is a much smaller one, but it still works out just the same way, right? And then from here to here, draw that line. It's a lot smaller. It's a lot smaller than the previous one, so things are going to get a little bit more crammed together, but it still works out just the same. Do my 45 over here. Go from this point across, like so, and then where it crosses right there, this now is our new point S. So here is S prime, right? So I've got one more point to go. Point R over here, right? I'm just going to take that one and give that a rotation. So Esther, again, right, if you're there in chat, please do let me know, because this is quite a painstaking amount of examples I'm doing for these questions that you were doing, right? And so I had another topic to get to, but if you're not, I don't know, if you're not able to follow, if you're not following along, maybe I'll wait and do that another day, and I'll carry on with questions for some other students there now. Right? But you can sound off there in chat and let me know if you want me to carry on doing these other examples. Join back up there. So now our point R prime is going to be this one here. So there's R prime. Now, I mean, this took a little while, It took a little while to get there, but we did. We got there in the end, right? There's joining those two. Join those two. These two. And these two. And there we go. We've got our new shape. We can see it. I'll sort of shade it in a little bit here, a little lightly shaded, just so we can see. There is our new sort of prime shape, right? The one after we rotated. Okay? So I hope that was very useful to you for the rotation method. Now, like I said before, there is another method that I can show you, sort of a shortcut one. If you want to check that one out in your book, right, I'll show you the page to go to. The page to go to in your book for this one is right here. This one, the method 2, the rotation rule. And this one shows you, oh, that was odd. This one here, the rotation rule, it shows you how you can sort of take a shortcut, sort of block counting kind of method, right? But like it says here, these ones are only going to work for rotating figures 90 degrees clockwise, 90 degrees counterclockwise, and 180 degrees, and only around the origin, right? So this method doesn't actually work for all of them. But yeah, I'll show an example of this one here now. And then, Betty Ann, I will move on to the topics for your work. But I'm just going to show one example of using this this method here, right? So say a question like 3a. So a question like 3a here, our points are, let's see, there's 1 here, and then point G is -2. Okay, so it's -2, 1. Yeah, they appear to use 2 blocks for each. Well, that's fine. We'll do the same thing too. All right, so that looks like -4, 2, kind of. Right, and then it's going to be up 2 from there, and right 2 from there. So I'm just going to take the points as they are sort of drawn on the grid that they have there in the book, not as they're represented by the scale in the book. So that's D, E, and G, right? And now the rotation rule, well, what does that one tell us? Well, it tells us a few different ways that we can sort of calculate these ones quickly, right? The rotation rule is what's over here on the side right now. It tells us that a 90-degree clockwise rotation, the coordinates are going to change from x, y to y negative x, right? But that's not the rotation that we're doing right now. Right? So the rotation rule, which I'm going to write out sort of down here. So let me zoom out and twist this a bit so we're, yeah, more on what it needs to be. So the rotation rule is if it's 90 clockwise, then our points, our coordinates, x and y, become y negative x, like that. They sort of switch and one becomes negative, right? If we're doing 90 counterclockwise, then x, y becomes negative y x. And if we're doing 180 degrees, which is of course neither clockwise nor counterclockwise, because it's totally around in the circle, then x, y is going to become negative x, negative y, like so, right? So that's our rotation rule here. And this one here is going to be a 180-degree rotation, so we're going to use this for our rotation rule, right? And that can enable us now to know where the new ones are going to be. So for point D in this question above, we have D's coordinates, the way I've drawn them, right? Not the way it's in your book, but the way I've drawn them, is going to be -4, +4. So it's -4, 4, right? And then that then is going to become 4, comma, it's going to be y Yeah. So it's x comma y becomes, oh, sorry, negative x, negative y. Yes, 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 of course. So it's going to be negative 4, 4, because we're using this rule here because we're rotating by 180. Okay. So then negative 4, 1, 2, 3, 4, positive 4, 1, 2, 3, 4. So this is going to be d prime here. Right? We can do the same for the other ones. For g, and g is negative 4, 2. So once that one swaps, it's going to be, well, so this is the x coordinate. So it's just going to become, yeah, it's going to stay there and become negative. So it's going to be positive 4 again. And then it's going to be a negative 2, right? So 1, 2, 3, 4, 1, 2. So this is now g prime. And we can do the same thing for e, right? So then point E at the start was negative 2, 4. Then we're going to use the rotation rule, again our 180-degree rotation rule, and just the two coordinates are just going to have their signs flipped, right? So then we're going to have positive 2, negative 4. So positive 2, negative 4, right here. So this is now E prime. Then we're going to go ahead and line those guys up. Like that. And there we have it. Right? So that is the way we can do some rotations using a rotation rule. Now remember, these only work it only works when the center is the origin, and it only works for multiples of 90 degrees. So there are ways to do a rotation like this just by using a rule like so. But if you are using a rule like this to do your rotations, you do need to write out the working. So I need to see this and I need to see this, right? Unfortunately, on a test or something like that, just eyeballing it and saying, oh, well, I think it's kind of going to be in this spot, so let's put it in that spot. That's not going to get you any of the marks on a test, unfortunately, right? I'm going to need to see workings either of this variety or this variety. And remember that this sort of question, this one would not have even been able to be solved by the rotation rule because this was a 45-degree rotation and a rotation about a point other than the origin. Now you can modify this rule to work for points other than the origin, but you can't modify it to do 45 degrees or 27 degrees or 108 degrees or anything like that. It can only do 90 clockwise, 90 counterclockwise, or 180. Okay, so then Esther, that'll be all that I'm going to do for that topic today. Again, I understand that was still a fair bit of information thrown at you for that, but hopefully now it's becoming a little bit clearer now that we've looked at it a few times, right? So now, Betty Ann, you asked me to do some other ones, and I had quite a few sections opened up, so you're going to need to bear with me just a quick second here while I try to recover from this second dastardly crash, right? Like, boy, not looking forward to the work that I'm going to have to be doing this afternoon now to figure out what in the world is going on with my computer. I've used it for plenty of high, resource requirement jobs in the past. It's never once had like an overheating problem, never once had a crashing problem, but now all of a sudden it's happened twice in the middle of streaming. So I mean, once is a freak occurrence, right? Twice is a pattern. So I'm going to have to figure out what in the world is going on and why. Anyway, yeah. So first up, you wanted some representing mixed radicals as entire radicals. Okay, so I have So we are going to do radicals, mixed radicals, entire radicals, simplified, and then some solving radical equations. Okay, so that'll be over here. So this is going to be Math 2101B, Unit 2. Right? And this is page, well, it's telling me it's page 8. It's not page 8. It's 183. And I'm going to do question 11. We see that one up there at the top. Express each mixed radical as an entire radical. Okay? So let me go over to the working display here. Zoom on in a little bit. Boy. Holy crap. This PDF. Oh my goodness. Okay. So 11a is 6 root 5. Now how do I combine these together? Well, say if we had if we were going the other way. If we were going the other way, it might be a bit clearer. So I'll show you going the opposite direction over here on the side, and then that might help indicate what we were going to do if we're going forward, right? So say we had root 40, right? Just as an aside. We know that we can call root 40 root 4 times root 10, right? And then what happens when we try to take this root 4 and move it to the outside? We actually take the square root of it, right? And we call this one on the outside 2 root 10. Right? Because we've taken this 4, taken the square root of it, and it became a 2, and then we took it to the outside. In the same sort of process, we can take this 2 and put it back inside if we really wanted to. We could take it, but then when we put it back inside, we've got to take the square of it, right? To be able to put it back in there. So we can do the same thing over here. We can put this 6 back in under with the 5 inside the square root, but we have to square it first. Right, so we can call this root of 36 times 5, right, which is going to be root of 180. Right, we could call it that. You notice how that your book says express each mixed radical as an entire radical. It doesn't say simplify it, because we're not actually simplifying. We're doing the opposite of simplifying. We're complicating it, I guess, would be the opposite of simplifying, right? That just makes sense. Yeah, all we're going to do for these ones is sort of put them back in under. Now, I know these are a little bit different than the ones that you were asking about from the assignment specifically, and I didn't see any exact ones in the textbook that would sort of show me a good way to go about doing those as an example, but I'm just going to make a few up here now. Right? Root of 1008 like that. Because what we're doing is we're taking the number outside, we're squaring it, which allows us then to put it back in under the root sign, like so, right? So say we had another question entirely that was x outside of the root of, I don't know, 3x, like so, right? We can do the same thing. We can put a variable back in under as well. Right? We just have to square whatever we're putting in has to be squared because this is a square root. So we can call this now root of x squared times 3x, which is the same as root of 3x to the 3, because we can go ahead and add those guys. Right? So these are a bit more like the ones that you were seeing, excuse me, in the activity that you're doing. Boy, oh boy. Okay, so imagine we had a question like this, right? And this is getting a bit more to the same level of complication that you are seeing in the assignment that you're doing, right? Say there was 2x squared outside of the cube root of 4x squared, right? And putting something back under a cube root is just the same as putting something back under a square root, just we've got to cube it now instead of squaring it. putting two terms, a constant and a variable back in under, again, just the same thing. It's just we're doing two parts at once, right? So it's kind of like this one and this one together, but really, it's not all that much different. Because now we say, well, the cube root of something is 2. What's that thing? Right? Well, 2 to the power of 3 is 8. So we know that when this 2 goes back in under the root, it actually becomes an 8. And x squared, when it goes back under this root, we're kind of raising x squared to the power of 3. Right? And x squared to the power of 3 is going to be x to the 6. And it's going to be multiplied by this 4x squared, which are already in under there. So this is then actually going to be the cube root of 8 times 4 is 32, and x to the 6 times x to the 2 is going to be x to the 8. Right? So we can put the numbers back underneath just fine, right? Back inside the root. Just we're going to have to do sort of the opposite to it, right? So most of the time we see them coming out, and for the vast majority of the times that you see questions on this topic, it's going to be like this and not like this, because this is simplifying and this is like complicating it. But that's not to say that you're not going to see this kind of a question sometimes. I'll just do one more quick example there. Say we had 7 x squared y to the 3 outside of the square root of 2x and z. I don't know, just to make it really, really complicated. Like, just imagine the most complicated situation that we're going to see in a question like this, right? All we've got to do is take the square of each of these terms individually, put them back in here, then multiply them by what's there, right? So what we're going to do now is draw the full square root out like this. 7 squared is going to be 49. X squared is going to squared is going to be x to the 4. Y cubed squared is going to be y to the 6. And that's going to be multiplied by the 2xz that were already there. And then we're going to get the square root of 96 x5 y6 z. Now again, right, that is a bit crazy complicated compared to what you're often going to see, but you could realistically see something like that for sure. Now again, do let me know at any point if you would like me to do some more on either of these topics. I'm going to carry on now and do, let's see, what did I say in the intro? Next was going to be, so that was mixed and entire, so now I'm going to do simplified. Yes, okay. So simplified radicals, just give me a quick second there to get the page organized. Wanted to do numbers 8 to 10, or at least parts of those. Yeah, let's do a few of these ones here. So back on over to my document display. So this is going to be page 212 again. Page 212, and this is going to be question number 8. Let's see, I did parts of question 8 already, didn't I? So I'm going to do 8c. I don't believe I did 8c or d yesterday. So that's going to be -3 outside of root x multiplied by root of x cubed minus 4x. Okay? So now we've just got to FOIL these guys out, right? We don't even really need to FOIL here per se, sorry, because this one is not a binomial. This is a monomial, and these are binomials, right? But I'm going to take this term and multiply it by both those inside, like so. Right? I'm going to end up with the -3 is going to stay here. Root of x times root of x cubed is going to be root of x to the 4. And that's going to be subtract, well, it's going to be plus, actually. It's going to be plus 12x times root x. Now, it does ask us to simplify, so we could go ahead and combine those together. Now, Betty Ann, part of the confusion from yesterday with the way that the book shows this is the rules for what's counted as more simple there or not sometimes is up to the writers of the book to decide, right? Like, do we combine these together and call this the root of x cubed? The root of x cubed? Or do we call this just 12x times root x? I would leave it just like this, 12x times root x. But we could combine these together the same way we did up here, say, and call this now 12 outside of the root of x cubed. So there's fewer x's represented. Now, to my mind, that's more complicated because generally when we're simplifying, we're taking things out. So I'm going to leave it taken out as much as possible. Root of x4, though, we can evaluate that one. That one we can actually get. So that one's going to be negative 3x squared plus 12x root x. And that is what I would leave that one as if we were using the sort of the root symbol like so, right? But it is totally possible that we could take this one and call it 12 root of x cubed, like that, right? Because this x, once it goes back and under here, becomes x squared, so it ends up being the same deal as what we saw up there. Right? So then let's do, did I do 8D yesterday? I don't think so. Either way, I'm going to do 8D now, whether I did it yesterday or not. Right? So 8D is root of x plus 2 multiplied by root of x plus 5, like so. Right? Now we're going to FOIL these ones. First in or out or last, right? That's how we multiply two binomials together. Root of x times root of x is x. Root of x times 5 is 5 root x. 2 times root x is 2 root x. It's not hard now, is it? 5 times 2 is 10. So this is x plus 7 root x plus 10. That's all I can do, right? That's it. Let's go do some of the ones from question 9. I don't believe I did any of the ones from question 9 yesterday. Right, and again, do drop a message in chat if there is anything that you would like me to cover specifically from these ones. Right, but I'm not going to cover the assignment questions exactly, just because, like, you know, it is important for you to do some of those so I can give you a genuine, good faith sort of grade on those, right? But yeah, I am totally willing to go through and do loads of examples of ones that are like it. So do, suggest any of these others to me that if you want me to go over them. What I'm going to do now is I'm going to simplify both these roots as much as we can, because like it's written, we actually can't add these things together at all, right? But I know from looking at questions like this one up here that I can take parts out of this one, right? Because root of 4x, well, I can call that 2 root of x, because 4 is a perfect square, so I can take the square of that. Then this 2 is going to stay out here, but 16, well, the root of 16 is 4. So I can put a 4 out there and call that root x. So what I actually end up with is 2 root x plus 8 root x, which is, of course, 10 root x, like so. Right? Then, let's see. Let's do, well, B is super simple. Yeah, let's do 9B really quickly. But I mean, 9B is one of my pet peeves about these kind of questions, is that, right, they give you in the book sort of the easiest ones you could imagine, kind of, instead of giving you the trickier ones so you can get used to them. But the root of x to the 4 is just x squared, so this is 4x squared minus 2x squared, which is 2x squared, right? The only difficulty there was knowing that the root of x to the 4 is x squared, which, like I keep saying, is something that's a lot easier when you start thinking of square roots as sort of fractional square roots, right? Because this would then, if we thought of this as square root as root of a half, this is x to the 4 over 2. And x to the 4 over 2 is, of course, x to the 2, right? Yeah, C and D I do want to do, though, for this one, because C and D are significantly more complicated and more like what you're going to see, or what you could see later on, right? So this is going to be 9C over here. That one is 3 root y outside of 4 minus 2 root y cubed, right? So then this 3 root y is going to multiply by both those terms inside. So we're going to end up with 12 root y minus 6 root of y to the 4, right? Because this is y cubed times root of y cubed times by root of y is root of y to the 4. And that's going to be 12 root y minus 6y squared. And that's all we're going to be able to do there, right? That's as simple as that question is going to get. Then if I look at 9D, which I'm going to do here as well, 9D is 5 minus root y, right? And then instead of just putting the squared there, I'm going to write the whole guy out. I'm going to call it 5 minus root y as well, because we're squaring it, right? We're timesing it by itself. So it's good for a one like this, like a FOIL question, to just write that one out. And that way we can go ahead and we can multiply our first, our outer, our inner, and our last, right? Like so. 5 times 5 is, of course, 25. 5 times negative root y is going to be negative 5 root y. And again, this is going to be another negative 5 root y. And then it's going to be a plus y. Because it's root y times root y is, of course, y. Right? That's kind of what it means. So this is going to be 25 minus 10 root y plus y. Oh, got a phone call again. Hold on a second. But okay, tearing through these ones a bit here now, but now I'm going to go down to solving radical equations. So solving equations with radicals, I'm going to go page 222, section 4.6, and I'm going to do a few of those ones. So let's see, page 222. Yeah, these are some good questions. So bounce on back over to my document display. Here we go. We've got our stuff all opened up again, ready to go. So let's see, question 6. Oh, we're zoomed in a bit far. Okay, so question 6a is going to be root of x minus 3 equals 5. So we need to state any restrictions on x, right? We should state restrictions here. So we know, of course, that we can't take the square root of a negative number. So we know that x has got to be greater than or equal to positive 3, right? And we know that because if x is anything less than positive 3, this part in here is going to be a square root of a negative. Now, it can be equal to 3 because we can take the square root of 0, right? But now, the way that we are going to solve each equation, well, what we can do is we can just square both sides, right? Because if these two sides are equal, once we square them, they're still going to be equal, right? Can you do some division ones? Division ones for which? For the simplifying radicals, you mean? Or for the ones like I'm doing right now? I'm going to carry on and do this one just while you explain that. Root of x minus 3 squared equals 5 squared, right? So x minus 3 equals 25, or x equals 28. So Betty Ann, do you mean like division ones, like say on back on page 212, maybe? Yes. Okay. Sure. Tell you what, I'm going to tear through. Yeah, some of the simplify ones. Okay. Yeah, I'll do some of those there now in a second. I'm just going to tear through a few of these ones here for 6, because you're going to see for the ones in 6 that these all sort of work out to be the same sort of method, which is, I mean, in a lot of ways, kind of simpler than some of the other ones. So I'm just going to go through and do these really quick. Now, I can just square both sides here from the start, right? but I could call this, I can move the 2 over so I just have the square root, which I like to do, and call this 5x plus 3, and this one is 11 over 2 over here. Then I'm going to go ahead and square both sides and call it 5x plus 3 equals 121 over 4, right? So then 5x equals 121 over 4, subtract 12 over 4. So 5x is equal to, is that going to be 109? 109 over 4? Boy, oh boy. What sort of a situation do we have here? So then x is equal to 109 over 20. Yeesh. All right. But that is, yeah. Simplify. Yes, yes, yes. I did see what you mentioned there. Yes, thanks. I did want to just quickly go over. Oh, this was C actually, not B. I did want to just quickly go over a few of these ones here so I can have them written out. And for B, say it's the cubed root of 4x plus 7 equals 3. Well, we just cube both sides. 4x plus 7 equals 3 cubed, or 4x plus 7 equals 27. 4x equals 20, x equals 5. Right? So that's all we got to do. That's all we got to do there with that. Yeah. So this one, yeah, that would work out. You could have left it over there like the other one. I will go back over now. Let's see here. So you wanted some division ones. So you would say ones like question 10 here. Okay. Question 10 or maybe question 12. To multiply each quotient by in order to rationalize the denominator of each expression. Well, just multiply it by most of the denominator. Yeah, let's do question 10 then, I guess, as you asked for some division ones. I think I did question 10 the other day, though, didn't I? I can't recall. I believe I did a fair bit of question 10 there. But either way, this is going to be back to page, what is this, 213? This is 213, right? Yeah. Question 10a, here like this. So that's going to be root of x to the 7 over root of x, right? And we can sort of put the root sign over the whole thing, right? We can call this root of x to the 7 over x, which is just root of x to the 6, which is going to be x cubed, like that, right? Because if we have one root divided by another, it's just the root of the the part under the root divided by the other one, right? So here's going to be the root of x to the 7 divided by x, which is the root of x to the 6, which is just x to the 3, right? And to say if we did, let's do 10b here. 10b is going to be root of 8x cubed divided by root of 2x. So I'm going to do some of these ones across here. So we can just do the root of the full thing, 8x cubed over 2x. Now, of course, from ages back, right, we saw ways to simplify these. 8x cubed over 2x. That's going to be the same as just 4x squared. And what's the root of 4x squared? Well, the root of 4 is 2. Root of x squared is x. So the root of 4x squared is just going to be 2x. Right? So this looked a bit more complicated than just 2x at the start, but that is what it reduces down to in the end here for us. Right, so let's do C and D of 10 there as well. Betty Ann, you can drop in chat if there is another one that you want me to do specifically, like this. These are, I gather, the division ones that you meant. But if there's any specific question on any specific page, do let me know what ones you mean. So again, right, we just write the root over the lot of it, 40x to the 4 over 2x squared, like that, 50, whatever. 50 divided by 2 is, of course, 25. X to the 4 divided by x to the 2 is x squared, right? Root of 25 is 5, root of x squared is x. So there we go. It's all we got to do for that. Yeah, let's do. I'll keep cramming it in down here below. So I'll do 10D as well. Question 10. So then 10D, you just make sure tendies. Ooh, chicken tendies. Something I haven't had in a long time. 6 root x to the 4 over 3x squared. Okay, finally. We finally got the one where there's a little bit more complication going on. Okay. So now we're getting somewhere. But, I mean, not really, right? Just at a glance, this one looks a bit different than the other ones we were doing, but if anything, it's easier, right? Because what do we actually have here? Well, what's 6 over 3? Well, that's just 2, right? And what is root of x to the 4? Can we simplify that one just from the start? Yeah, of course we can. We can that's just x squared. So that answer is just 2. There are other ways we could have done it. Like we could have squared this and put it under a square root. We would have had root of x to the 4 over x to the 4, which of course just makes 1 as well. So that one there is just going to work out to be just plain old 2. Right, now I'm not seeing any other ones on this page that would be super good examples of the division ones. But yeah, do let me know if there are other like specific division ones that you want for the simplifying. But all it really breaks down to is that, we're dividing what's under both roots, right? Then, yeah, I wanted to do a little bit more on this last topic over here just to show some of these ones, right? But yes, because 8B and D, I wanted to show at least one of those. Right, okay, yes. So this is going to be back to page 222. Right, and the reason I wanted to show these ones specifically is, well, we'll see now in a second, but I wanted to show how we need to get rid of some of the other pieces before we can go ahead and do the squaring of both sides. Number 4, page 212. Okay, yes, I believe, yeah, that is the exact one that I did yesterday. Okay, sure, I can go down through this one again. But now you are aware, you do recall that the answer in the back of the book for 4A is indeed wrong, right? It's going to be Math 2101A, Unit 2. Right? So if I go down through 4A here, we have 5x cubed root x multiplied by the cube root, the square root, sorry, of 2x cubed, like so. Right? So what we're going to do is we're going to multiply what's in this bracket by what's in this bracket. So what we're going to do is I'm going to keep all the same stuff in under the square root sign, and I'm going to multiply those ones together. So this is going to become 5x cubed, because this is just going to stay out here. We haven't done anything with this. Then underneath here, we're going to have the root of x times 2x cubed, which is going to be the 5 and the x cubed stay out here. Nothing's happening with them. This is going to be the root of 2x to the 4, right? We can't take the root of 2. We can take the root of x to the 4. So it's going to be 5x cubed, x squared, root 2. Then this x cubed has not gone away, despite whatever the book thinks might happen. So it's going to be 5x to the 5, root 2. Right? So then 4b, we carry on with these ones. Negative 5 root x multiplied by 2 root of 8x cubed, right? And really, the rule that we're doing, we had to remember, the stuff outside gets multiplied by the stuff outside the root, the stuff under the root gets multiplied by the stuff under the other root. So negative 5 times 2 is negative 10. Then under the root, we have 8, and then x times x to the cubed right? X to the cubed, x to the 3, which is going to be x to the 4, right? And that's going to be negative 10. Yeah, I'll tell you what, I'll just write this out here now. 4 times 2 times x to the 4, right? Because we know we can break 8 into 4 times 2, and 4 is a perfect square. So now we're going to have negative 10 times 2 times x squared root 2. So it's going to be negative 20 x squared root 2 for 4b. Right? So then for C is going to be negative 36 root x cubed over, and this I did this one yesterday as well, I recall, over x, right? Negative 36 over 12 is negative 3. And then this is going to be the root of x cubed over x, which is negative 3, the root of x squared, which is negative 3x, like so. Right? Now, 4D actually gets on with a little bit of complication, but still not a ton compared to some of the other questions that we've looked at in this course so far. I'll put that one down here, I guess. So 4D, it's going to be 3 root x multiplied by 4 root x cubed over 6 root x to the 4. Now, again on top, right, we're going to multiply these guys across. It's going to be 3 times 4 is going to be 12 here. Root of x times root of x cubed is going to be root of x to the 4. And that's going to be over 6 root of x to the 4. Right? Now I could call this root of x to the 4, that's the same as x squared, but it's over itself already, so that can just cancel with that. This can mostly cancel with that and make it 2, so we're going to be left with 2. 2 is our answer. Just a 2. That's it. That's it, boy. Right? So that's all there is to the ones in number 4. Right? They're not, none of those are very, are particularly complicated questions for what you've got to be doing in this unit. Right? So, like I said, I did want to show page 222, number 2 of the ones at least from number 8. So I would like to show this one just so that you're well equipped to tackle that assignment that you showed me. Page 222, 8. I'm going to do 8A, and I'm going to do 8C at very least. Okay? So back over here now for 8A. State any restrictions on x and then solve each equation. Well, so this is the root of 2x plus 17 equals 5. Now our restrictions on this one is going to be that 2x plus 17 must be greater than or equal to 0, right? Because this is our restriction. It has to be greater than or equal to 0 because we can't take the square root of a negative. So we had to do sort of like a mini algebra problem on the side to figure out what the restriction is on x. So remember that an inequality works exactly the same as an equal sign. We can move pieces around it left and right, just like we would an equal sign. So this is going to be 2x is greater than or equal to negative 17. So it's going to be x is greater than or equal to negative 17 over 2. So there's your NPVs, or your non-permissible values, for this question. Right? But now to figure out, sort of actually to solve the question, we're going to go ahead now, we're just going to square both sides like we did before for the other one. Right? So it's 2x plus 17 equals 25. So then that's going to be 2x equals 8. Then x equals 4. That's it. That's all we got to do for them is that. Look. It's just that right there. Look. 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 Yeah, what does a Newfoundlander call a moose? Law, law, law. What does a Newfoundlander call a baby moose? Ah, law. Right? That's about right. So then for question B, actually it's not C, is it? It's B. B I wanted to do. I got messed up where these guys go down in columns, right? I'm used to reading from left to right, not up and down, up and down, up and down. Anyway. So for b then, where I'm going to do 6 minus 2x, it's the cube root of that, plus 1 equals negative 1. Now, we could go ahead and just cube both sides from the start, but it's going to be a bonkers amount of work, right? Because on this side, we actually have the part that's under the cube root and another bit right here. And this is why I wanted to show this question right now. Because we could, just from the start, go cube both sides. But my God, the amount of work we're going to have to do is insane. Because we're taking this and multiplying it by itself twice. We're going to have 3 binomials multiplied together, which is going to be a ton of work. So why do that? Why not make it easier for ourselves? What we should do anytime we see a question like this is make sure that the only thing on the left side of your equation, or on whichever side of your equation, is the root that you're cubing or squaring or whatever. Right? So I got to get rid of this plus 1 because that is really being a shit disturber there, to use a phrase that was taught to me by my first year math prof at Munn, CZ Koo. Right? He called it a shit disturber. But apparently someone went and complained. Someone went and complained to university admin that this professor was using foul language like the word shit. So he had to stop doing that. He had to stop calling them a shit disturber. But in my mind now, ever since then, that's just, he's really drove that one home. These are called shit disturbers. And you got to get rid of shit disturbers. So this is going to be cube root of 6 minus 2x. Now I'm going to subtract the 1 from both sides. So it's going to become a negative 2 over here. So now I'm going to need to cube both sides, right? So if I cube, I'm going to write this out with the bracket around just so we see what I'm doing. Right, and now I'm going to go up over here to carry on with this question because I've run out of space. So that's going to be then 6 minus 2x on this side, and over here it's going to be negative 2 cubed. Well, what's that going to be? Well, it's going to be negative 2 times negative 2, which is a positive 4. And that positive 4 is going to be times by a negative 2 again. So it's going to be a negative 8 over here. Right? So then I'm going to switch these two for the sides. I'm going to have 6 plus 8 equals 2x. Or rather, 14 equals 2x. Or 7 equals x. Right? So the essential thing for you to know here, right now, is that whenever you see a bit like this, we got to get that guy out of there. Right? Because that guy is really going to mess us up a bit. Tell you what, I'm going to go back over to the same page that I was writing on before, and I'm going to go ahead and do 8C over here on this part. And of course, like I do before, I'm always going to send you all of these ones. Oh, geez, why? I can't. Okay. Letters are not my strong suit. I might have a master's in English, but letters are not my strong suit. So that's D. It's D that I'm going to do, right? So that one is going to be 33 minus 6x. It's going to be the root of that plus 4 equals 13. Now again, right, just like we said in the last one, we can go ahead and square this, but it's going to be a bonkers ridiculous amount of work because we're going to have this whole root times by this plus 4. We're going to have like 8 of these put together. Then we're going to have a 16, and we're going to have this one squared. And we're just going to end up with a mountain of extra work to do that we don't need to be doing. So what I'm going to do is simplify this side by getting rid of this plus 4. Right? So now we're going to call this root of 33 minus 6x. And really, when I say it's a bonkers amount of work to do, what I'm actually saying is that it's actually not going to work out like at all. I mean, you can try it and you'll put in a ton of time in trying to figure it out. Eventually you'll get to a point where it's like, I can't go any further, right? And then you just got to go back and do this again, kind of, just to get it right this time. But, I mean, it'll sort of work, but it's a really, really, really roundabout way to get there. When you could, just from the start, get rid of this guy, subtract it over here and make it a 9. Now it's easy. Now we just square both sides. Now this is a step that you don't necessarily need to write out, but I'm writing it out just so you can see. Minus 6x is going to equal 81. Now we've got a fairly simple problem like we've seen a whole bunch of times before. Negative 6x is going to equal 81 minus 33. Negative 6x is going to be 48. So x is going to be 48 divided by negative 6. So x is going to be negative 8. There we go. Right? So again, the important part when you're looking at a question like this one, like 8B and D, the reason I wanted to show you those is because it's imperative that you get, which is a great word, it's imperative that you get rid of this extra linear term, well, this extra constant rather, sorry, not a linear term, this extra constant, you get rid of that before you start doing your squared, or you're just going to make a ton more work for yourself and you're going to be back at square one um, after doing a whole bunch of other algebra that you didn't really need to do, right? But that, I believe now, has finally brought me to the end of what I wanted to get to today. Boy, I had a lot laid out to get to today, didn't I? Look at that. I mean, we did have that crash again, which I am now going to have to go and not only am I going to have to go and stitch my video back together so I can put it up on YouTube sensibly, but I'm also going to have to go call in Microsoft support, I guess, and try to see what I can do about that error message that popped up. But yeah, boy, oh boy. The things, I mean, you know, 48 days with one hit, well, 47 days with one hitch, now 48 days with two hitches. It's the number of hitches per day is increasing rapidly. So I'm going to have to start seeing what I can do about that, I suppose. Yeah, thanks for being here with me on this lovely Friday afternoon. Looking out at the like I said when the stream started, these views that sometimes take for granted, these views right in our own backyard, right? I mean, not directly in my backyard, although my backyard is fairly nice, right? It's got a nice view of Waterford Valley, but having a view of Waterford Valley is not quite the same as having a view, from Dead Man's Bay Path over here, looking out and seeing the saltwater bay that we call freshwater bay for some strange reason, right? But it's views that we have to appreciate while we have them, I suppose, because it's not going to be there forever. We're not going to be there forever. One of the two, both. I mean, it's going to take a long time before the view in Newfoundland goes away, but it will eventually, right? Newfoundland will be, I don't know, crammed into some new mega continent once the continents shift again, right? But anyway, that'll take a while. I'll definitely us and myself and everybody I know and everybody who they know is all going to be gone before then. But maybe sooner than that too. Anyway, thanks for being here and hanging out. Yes, Betty Ann, enjoy your weekend too. Hope you have a great one, nice relaxing one, maybe to take a bit of time away from all the trying math work. But thanks for being here. I hope to see you again Monday, and stay safe out there. See ya.